Hello everyone, my name is Łukasz and I'm developer at VirtusLab. I wanted to start with a question to the audience. How many of you are DevOps engineers or site reliability engineers or just, plain operations engineers? Okay, that's great. Some of you actually know what we're going to talk about, so that's cool. Okay, the obligatory about me slide. I'm principal software engineer at VirtusLab, which means basically that I'm internal consultant and I'm jumping between projects. I'm doing Scala, functional programming, distributed systems, so akka and stuff related to akka mostly. Let's go through a quick agenda about what this talk is going to be about. First, I'm going to quickly introduce you to the domain of infrastructure as code and the tools that exist in this domain and what has been already built in this domain, how it works. Then I'm going to introduce the newest kid on the block, which is Pulumi, the programmable infrastructure as code tool. Then we are going to do some deep dives into the Bison, which is the purely functional Scala SDK for Pulumi that we have been developing at VirtusLab for last almost year. And we're going to finish up with some comparisons between existing Pulumi SDKs and some notes about future directions for the project, where we want to go and where we want to take it in the future. So let's start with the infrastructure as code tooling. Let's start with the genesis of the whole domain of those problems. So why do we need tools that allow us to do infrastructure as code? The first thing is in bigger companies, there is an actual need to reduce manual operations, reduce manual interventions into the infrastructure. Because what you get if you are doing manual operations, well, you get snowflakes, you get mutable servers that evolve into big heaps of mud that nobody really remembers how they operate, and then you do something with them. You do operations, you do deployments, and stuff basically explodes because everything is unique and melts when you touch it. So the need to reduce those manual operations also brings the need to enforce the environments to be homogeneous. We want everything in infrastructure to be as similar to each other as possible, so everything is consistent and the operations can, we can just use the same code to perform the same operations on all environments. So how those tools work? It's quite simple. You, in most cases, describe the outcome. You describe the desired state of the infrastructure that you want to get in the end. And then the tool does its magic. It applies your demanded state of the world on the actual mutable, imperative, horrible world, so that the outcome suits your desires. It matches what you wanted. And most of those tools also track the state of transformations that they apply to be able to detect when something is different from what they expect that to be. So if for instance, somebody did a manual intervention, those tools, at least some of them, try to find out that, okay, that doesn't really look like when I was last touching it. So it also keeps the state of the transformations. So let's go with the timeline. The Puppet was the first widely adopted tool. It came out in 2005 and it tried to solve the problem with this beautiful DSL, which doesn't really look like anything that anyone knows really. And then, well, Chef came out because Puppet had some issues. The market addressed the problem. Chef introduced a new big idea. Let's, misclicked, sorry. Let's introduce actual programming language to the table. Let's, give the ability for the user to use programming language, but, let's bolt on a Ruby DSL on top of that and just call it a day. So stuff looked like that in Chef. Then we had Ansible, and that's when, simplify things movement started, gaining voice, and that, resulted in something that I find quite horrible, which is, let's do YAML, because what can go wrong if we just do YAML? YAML is perfect for stuff that is mission critical. And problems and troubles come in pairs. So SaltStack was also released in the same year in 2012, and it also made the same solution, let's call it, which is let's use YAML and you just type everything in YAML again. Then it was early 10s and cloud was gaining hype. So market addressed the problem. Terraform was released by HashiCorp, and Terraform was a bit different. The previous tools were about provisioning and orchestration of servers, while Terraform was about mostly management of cloud resources. So Terraform had a bit wider domain, but it was also introducing a new fine DSL on top of everything, which is called HCL, and as you can see, it's also very nice. It's declarative, but it's also very nicely typed. And then things got even funnier because Google released Kubernetes, and Kubernetes ushered us in new era of awesomeness. So the stuff that is perfectly well designed for large-scale mission-critical deployments and just works because it's simple. So all of that stuff was perfectly understandable, trivial to maintain in long term. And as we have so many DevOps here, I want you to find a bug in this because it's trivial, right? So anyone? Any takers? Manager is telling you to deploy stuff to production. Where's the problem? Okay. Okay, so.
Deployment and deployment.
Cool. Yeah, I applaud your PTSD. Yes, that's the problem. There's a typo. There's the second bug.
Much labels up and here selector is.
Yes, that's one problem. There's the second one. Where's the second one? Okay. No, that's fine. I mean, probably not fine, but no, it's the target port. The service is actually targeting 8080 and the container is exposing 80. So good luck. You will try diagnosing endpoints. Nice. So we have some issues with that. And first, everything is stringly typed. And starting with Ansible, we get YAML. With Kubernetes, we also get YAML because why not? And YAML is, in my personal opinion, is the worst possible thing to do in this regard, and it has a huge mistake potential. There are so many footguns that I just don't even remember all of them. But there were things that were okay. Most of the stuff was declarative, and that's basically good. We want to describe what we want to do. But in the same time, most of those tools had the problem that you declared stuff, but unlike SQL engines, you didn't get an error up front. It just started executing stuff and then weirdly broke and exploded in runtime. So that was a problem. And also, if you are doing declarative stuff, declarative programming, you have to do stuff that allows users to actually be able to express their ideas, express stuff that they need to do to get things running. And with those tools, expressivity was limited. So in Virtus Lab, we have quite a lot of experience running big enterprise platforms for our customers. And we found out the hard way that YAML and Bash are probably not the best ways to do that. They are not really helping you build stable platforms. With Kubernetes in particular, we found out that doing YAML is very, very bad, as Kubernetes is very lenient. It allows you to apply stuff that doesn't make sense. So it will only crash and burn when you actually apply stuff, and then, well, you get alerts. So our thinking was, can we do better? Can we do something that would be good? And we were looking in the space, and that's how we found out Pulumi. Pulumi came out in 2018. It was started by Joe Duffy from Microsoft. I think some of you might recall him as, I think he was the leader of Midori project in Microsoft, which was, I think, a managed operating system. Not sure. And they started the company, I think, in 2016. came open source with the project in 2018. And Pulumi is a bit different in almost all regards. So the new thing, which is not really new because Chaff did it before, is that you can use your favorite language. You don't have to use Ruby. I don't think there is an SDK for Ruby anyway. But you can use your favorite language except Ruby to actually describe the infrastructure that you want to get. And you can use full-blown programming language with all of the constructs that you know, that you use, that you love, maybe. So we can get a quick look into how a program in Pulumi looks like. And we start with the fact that it's JavaScript. Sorry about that, but it's the most commonly used SDK, and it's also sort of functional. So we start with declaration of what we are going to use. So we require the Pulumi package. We require AWS package, and then we basically use our RPC call to get MII image ID. So the line with the then result ID gets the result ID from the response from get MII function. Then we declare a security group because it's cloud. We have to declare a security group, blah, blah, blah. And then, well, we do stuff that we want to do. We actually create an EC2 instance with the actual MII, with the user data provided as a script, and we can export stuff. Exporting stuff is a Pulumi concept because every Pulumi program is called a stack, and stack is an instance of this program. So you can think of a Pulumi program as a blueprint that you instantiate, like a class, basically. So you get an instance of a stack, and that means that you can have multiple environments using the same stack, and you can basically work that way. You can iterate on that. So how Pulumi makes it happen? Pulumi is, as my colleague called it, a non-trivial microsystem. So what it means, it actually starts multiple processes when you run it. There is the Pulumi CLI, which is the deployment engine, and does most of the work. It is responsible for running the user's program. It is responsible for ordering, resource creation. It does parallelization, so the stuff that can go in parallel goes parallel thanks to Pulumi engine. It also manages state, and well, it uses the language SDKs. What are language SDKs? Language SDKs are libraries that are built in given programming language on top of gRPC layer that talks with the Pulumi engine. And language SDK has one role. It has to expose familiar, let's say, DSL of Pulumi to the user. So it has to provide the primitives, the building blocks of Pulumi programs. How does Pulumi work with multiple providers that have different APIs? So they do the same thing as Terraform, basically. They have schemas, pictured here as package schemas, and they have code generators. So code generators take those package schemas and they output full-blown libraries that have all the resources that you can and functions that you can call in the APIs of the cloud providers. And not only cloud providers, you can manage whatever you want. So when you actually start this program, let's go into that. I have a small example of a program that doesn't do anything really very interesting. It just declares two S3 buckets, one for pictures of cats and the second for pictures of dogs. And we are just exporting the URLs because you want to know what you have declared. You want to know where to send those images. It's a very rudimentary example, but I think it manages to send the message through. So let's go through what happens when we actually start Pulumi. So the first thing that starts is the Pulumi engine, and you can see in this beautiful sequence chart that the first thing that happens when you run Pulumi up is that it actually starts user's program. It does some configuration on the start, but it's not very important. And the user program, I'm going to switch back. It actually goes, the main thread, let's call it. It's not JS, so just a single thread. It goes through the declarations of your program. So it first notices that, okay, then there's a cats bucket to be created and dogs bucket to be created. And then there is an export. So it's just a value, and it's a value of output type. It's quite important. We will get back to outputs, but that's all that it has to do. It just has to call two constructors for S3 bucket, and then just bind values that are properties of the object that is resulting from the constructor to those export contents. So what happens underneath? And this is quite important. Pulumi is basically fully asynchronous underneath. The engine is fully asynchronous. There's nothing really blocking here. So what happens when you call a constructor is that the constructor does a nasty side effect, which is calling RPC underneath. And it registers the resource and then just returns control, because it's asynchronous, to the main thread. So without waiting for any response from whatever is on the other side of the wire, we are just going to the next declaration of the docs bucket, and we are just registering that. Asynchronously, the Pulumi engine, after getting the first request, it validates the state, it checks what can be done in the stack, what are the realities of the environment that was already built. And if everything is fine, it actually executes the CRUD request to a service provider that it has already started as a separate project. So we already have 3 projects. I mean, 3 processes. Then, things are asynchronous, so the second request for registration of the bucket for docs arrives, and the engine does the same thing, validates stuff, executes the request to the service provider. Then we have to wait, and there's a quite important thing. The main thread, so to say, completes the program. It doesn't do anything else. So all the stuff that is happening afterwards is completely asynchronous, and it's basically operating on callbacks. So after some time, eternities, when it comes to some service providers for cloud providers, we get a result for our requests, and they arrive. I don't think the order is guaranteed, but maybe it is. We get responses for those requests, and Pulumi engine redirects those responses back to our program, and that allows the SDK for your language to actually resolve those values. So what it means that there is a value to be actually exported as the website endpoint for both cats bucket and doc bucket. So what happens then is, it's a minor implementation detail. These exports that you have on the end, they are actually properties on a resource that is called stack, which is your program. Your program can have output properties, which basically mean that your program can be used. This is composable architecture. So your stack can be imported in another Pulumi program, and this another Pulumi program can use your output properties. So cats on dogs and stuff like that. And what happens then in the sequence chart is that after the registration of those stack outputs, your program is completely shut down. It completes its work. There's nothing more to do. Pulumi engine does some internal processing that it has to do, and also shutdowns. You get complete infrastructure, and you get a chart, not a chart, but a list of stuff that was done. So let's analyze this a bit, because we have this slide where we have outputs, and let's go into outputs, because outputs are, from our perspective right now, the most important thing here. What is an output? So an output is the main pseudomonad. I'm not sure if there is any CT specialist here, but I don't think that pseudomonad is a practical term in CT. But it's a monad that is not really conforming to the laws of a monad. And why is that? It's caused by the fact that outputs are generally implemented in all the SDKs in terms of things like promises. So we have promises in JS, we have tasks in C# implementation, we have completable future in Java implementation. We even have their own implementation of something similar to a promise in Go on top of coroutines. So that's quite interesting. But the fact is that if you are doing something like that, if you are using single write asynchronous data types, that means that output is effectively memoized. And that means also that, well, like all of those constructs, it's eager. So if you start it, it starts running. If you start running completable future, it just starts running on another thread. So that's a big thing to consider, and we had to take this into account while designing an API for purely functional Pulumi SDK. So there is also another, problem with the fact that if you have eager code and you have asynchronicity, you're not using nodes, so you have the possibility of using multiple threads. There are all the problems that are, related to the fact, and those are the problems that we want to avoid because side effects that are unconstrained in concurrent environments are quite bad. So, what we get from using Pulumi? So, what are the benefits of using this tool in the end? So, Pulumi has some very nifty and nice features. You can, for instance, define your own custom components. You can define your own pieces of infrastructure that use some of the resources that are exposed by provider SDKs. So you can create pieces, reusable pieces of, reusable blocks of multiple resources that are welded together. And given that you are using full-blown programming language, you can make guarantees about the fact that those things fit together. They can't be broken. They won't explode in a weird way. So you have logical components. You also have ability that I think no other tool really has right now, which is the fact that your programs, your Pulumi programs, can be embedded in other applications via something that is called Automation API. And that means that, for instance, you can expose your program that manages your infrastructure programmatically in a REST endpoint. You can do something like that. So, for instance, we could, expose this small program that we have that creates buckets for dogs and cats, and make a REST endpoint that later on. For instance, allows you to create buckets for another animal. There is also a project that is called, I think, Pulumi CrossGuard, that allows you to do something very interesting for those of you that live in big corporations, especially, because it allows you to enforce policies for all the managed resources, which is quite obvious when you think about it. Pulumi allows you to read and modify, update state of resources that it manages. So why couldn't you just tell it to fetch all the resources and apply this function that I have in my programming language that checks whether this resource complies to the corporate policies. So CrossGuard allows you to actually verify that everything that you have done fits to the corporate policies that you have. So, oh my God, what is that? I have no idea. It worked on my machine. Anyway, we are Scala developers at Virtuous Lab, and we are quite happy with Pulumi as it is. But we have this, let's say, issue that we want to reinvent stuff and do stuff in our way, in a way that we think that is the best. So we started an initiative after we completed implementation of Pulumi Java for Pulumi. That was our first step. We built Pulumi Java. They incorporated that into ecosystem, and it's now a fully supported language by Pulumi. So Java is there, and it was built by one of our DevOps engineers. After this experience, we decided, okay, that was nice. Let's build something less trivial. Let's build something that is more secure and less verbose. So we started the project. We called it Bison. Bison means basically a broom, which fits because Pulumi is also, I think, broom in Hawaiian. I hope I got it right. Anyway, and it's basically a Scala SDK for Pulumi. What were our main motivations? So we already have the experience with maintenance of cloud deployments, and we know that with time, stuff erodes, there's bit rot, and people change teams, knowledge evaporates. There's a lot of problems with ongoing maintenance, and if you can get problem from the compiler, if you can get some invariants handled by tooling, you should do that, especially in mission critical software. So that's the problem with current solutions. They are basically either too constraining or too brittle or both. And we already had an idea that we want to do that. We've built a similar project like Pulumi, but it was limited in scope. It was just for Kubernetes. We didn't really have the idea how to scale it to another set of providers. It was called infrastructure as types, and it was basically a way to describe infrastructure on top of Kubernetes as types. So you basically had some primitives that were fully typed, and a DSL that allowed you to compose those primitives in a way that you had fully typed and composable components. That basically checked the invariance between things. So you couldn't, for instance, connect, let's say, SNS to application that was only exposing HTTP endpoint, because that doesn't make sense. And in the end, well, like I mentioned, we wanted to manage infrastructure with a language where if it just works if it compiles. So what we had to do. So on this chart, the first thing, the most obvious, is that we had to build a language SDK for Scala. We had to build support for the primitives that allow you to build Pulumi programs. On top of that, to actually do anything productive beside just running programs that don't do anything, we have to have libraries. We have to have providers. And that is, as I mentioned, done by generating code. So we took Scala Meta project and we wrote our own code generator, because Pulumi does that in Go. And we are currently in the process of tweaking this so that the largest APIs like AWS, Azure compile correctly, and we will get those plugins. We'll get those providers. What were the objectives of this project? So what we wanted to do from the start. So the first thing was that we wanted to use Scala free, because there are lots of improvements and lots of nice features that we wanted to leverage, mostly metaprogramming, but we'll get to that. We also wanted to do what Software Mill's ecosystem does. So we wanted to support all of the Scala ecosystems, as Scala developers are picky, and you have to tend to all of their choices and tastes. So we wanted to support both functional ecosystems and less pure functional ecosystems as well. And well, the obvious thing is we wanted to make everything more type safe, and also we wanted to avoid some of the foot guns that we have already encountered in Pulumi APIs that already exist. And what was the core, let's say, value in this was that we wanted to focus on developer experience. This was the most important thing for me personally in this project. We wanted to make the experience glorious. We wanted to make things seamless without any, weird stuff that you don't understand that you have to deal with. That led us to some architectural decisions that we had to make. So the first was that if we are going to support effects, if we are going to support cuts effect and ZIO, we will probably also have to be purely functional from the start. Second thing was that we want to use the same idioms that all Scala programmers know. So we wanted to use map, we wanted to use flat map, we wanted to use sequence, we wanted to, which is traverse, we wanted to make it almost, indistinguishable from normal Scala programs. And we wanted to make it, fit to existing applications. So you can just drop a piece of Bison application into your existing application, provided that you're on Scala free, and just have it working. And we also wanted to leverage the new capabilities of Scala free in terms of easy metaprogramming and easy generic derivation to minimize the problems that other SDKs have, because most of them use reflection to actually integrate the language, the host language, with the serialization layer from protobuf that they use. So we wanted to leverage metaprogramming and make things very, researchy in the internals, but very simple in public APIs. And the biggest problem in the start of the project was, how do we deal with CATS effect IO? How do we deal with Zio and future that we want to support in the same time? So this was the end result of a month, I think, of experimentation. We tried tagless final encoding, but the problem was that there was no easy way to actually hide it from the user, and that was something that we desperately wanted to do. We didn't want to make the user deal with F-type everywhere. That was a big no-go. So once we started building the API with tagless final, and it actually bubbled up to the layer of user program, we said, no, okay, that's not going to work. So we went towards the original idea that was, let's just build something like a free monad. And this came out as a result. It doesn't, do the most beautiful thing, as you can see in the suspend case. Here we are basically expecting it to evaluate whatever to a future, Scala future of A, which probably isn't the, nicest thing in the world, but actually we do that at the end of the world. So maybe it's not that bad. So I asked Mateusz Kubuszuk, who sadly isn't in this edition of Lambda Days, to try and explain this in a more formal way. And this is what came out from Mateusz Kubuszuk GPT. So this is a free algebra that defines the execution operations as data. Okay. All the target effects, so CATS effect, future, and Zio, have to implement an instance of a type class called runtime that interprets results at the end of the world. So only when the whole program is composed, we actually trigger run on runtime. It's obviously a monad, and it's a lawful one. And it's also an equivalent to a free monad, which is a free of S to A, where S is our fixed algebra describing our operations. The programs that users build don't interface with result. That was one thing that we wanted to do, and we wanted to hide it. We wanted to hide the integration layer beneath APIs, so all the user programs are actually built in terms of outputs. Outputs are defined internally, just like they are defined in other Pulumi SDKs, as wrappers around result or completable future or task or a promise of output data. Output data is internal Pulumi data type that actually implements the semantics that are necessary for Pulumi programs to run. User can use any effect library that has an implementation of result to future type class that is necessary to do that. So you can quickly, I think, understand that we are basically catching the result and an instance of the type class, and at the end of the world, we are just unsafe running that to future. So that means that out of the box, we support Scala concurrent future, we support CATS effect IO, and we support Zio. This is how the API in the current iteration looks like. So this is Scala free, and we have Pulumi run that, for those of you that don't know the new syntax, actually takes a lambda. So Pulumi run takes a lambda, and it's actually a context function. So what you don't see here, that's good actually, is that there is an implicit context available in the scope, and most of the functions that you see in the API, they actually take this implicit context to actually scope the program, because in automation API you want to scope the executions. That's something that's a problem for many of the Pulumi SDKs because they have mutable shared state. We don't. We just have a context that is created per instantiation of the program. So we have the same program. It's just creating two buckets, one for pictures of cats, one for pictures of dogs. And it also exports those URLs. Nothing fancy, we have for comprehension, which already should tell you that the bucket function returns an output. And output is a monad, so we have to compose them. So there are differences between our approach and what Pulumi does. And first is that we don't use constructors. For some reason, constructors were used in most Pulumi SDKs. I'm not really sure why. Maybe it was to build this illusion that everything is synchronous, but it really isn't. There are asynchronous things happening underneath, and we didn't really want to hide it so much because we are fine with monads and we are fine with asynchronicity. So we use just plain functions as resource constructors. And there's also the problem that everything is lazy, everything is purely functional. So that means that we break away from usual execution of Pulumi program. So for instance, if you leave a dangling effect, so you just bind it to a value, but you never compose it into the rest of your program, it's a problem. Pulumi will never see this resource. So okay, that's one problem. We can do maybe not very pure thing, but we can register all the calls to the resource constructors. We generate them, and we also use the context underneath to actually do all the work. So we can, register the call and maybe crash or just warn the user about, you left a dangling resource there. Is there something that you wanted to do with that? So that's one thing that we want to do with that. There is also a conversation that maybe we could do something about eager evaluation of the result data type. So maybe we could do an opt-in impurity on top of that. So it would basically, if we had that, 5 minutes, okay. If we had that, we would get basically the same semantics as all the other SDKs have. So you would just describe things, and you don't even have to compose them, they just run. So they are just running. They are just evaluating on their own, and all the callbacks will be executed. You don't have to compose them. So those are things that are different. And let's go quickly through safety features that we have. So this is a piece of actual integration testing program that we have that runs because Kubernetes API is done and we have it working. And it declares a namespace called liftoff, and it declares a config map that is later used for Nginx to actually serve this page. So the first thing you can notice is that we have resource constructor called namespace. It doesn't take any additional arguments because you don't have to provide any when you're creating just a namespace in Kubernetes. The namespace is then used in the configuration of config map because you have to put the namespace in the meta data for the config map. So you can see that we have a little problem here because this program isn't, composed in the for comprehension out of the box, and you don't get unboxed values out of the monadic context. So it means that when you want to access metadata from the namespace to get the name, you have to do flat map, and that's not very pretty. Resources are case classes that have all fields as outputs too, so you have to flat map first and then map on that output to get the actual value. Not very pretty. Pulumi is built in a way that allows you to deal with this because they assume that they want to emulate synchronous programs. So they have a feature called lifting. So let's assume that we have this namespace, and as I described, we have to do this chain of flat maps and maps to get the value out of that. But there is a syntax that Pulumi implements in some of the SDKs that is called lifted syntax. Don't ask me why it's called lifted syntax. Basically, it allows you to address those fields as just properties on the object, but we know that the app namespace is actually an output of namespace. So how do we do that? We had a clever way to do that, and we were using a lot of metaprogramming to get it working with dynamic Scala programming capabilities. It was a nice prototype, but then one of our compiler team members came up with something simpler. Why don't you just use extension methods? You are already generating the code. So let's just generate those methods for the particular complete types and just, be done with it. And that's what we did. It actually worked pretty fine. So what you get here is that metadata is a property on something that is in output of namespace. So you can call the method, then you call the name method, which is again an extension method on output of metadata, and you get an output of option. But one of the parts of the semantics of Pulumi is that outputs contain optional values already. So output of option of something is sort of like option of something. So we can, if we want, obviously, call a flatten on it, and it will just flatten it and pass the optional down to the output layer. So here's the updated example, and you can see that it looks sort of better, and I think that it's a nice gain in terms of usability, and yeah, that's what we wanted to get. There's also the component API, which is quite important, and that was the biggest pickle that we had, because it is kind of, food gunny in Pulumi. This is JS SDK, and basically all official SDKs follow the same pattern, and it's forced by the fact that they are using constructors because they want to use new. Scala 3 drops new, so for us it was basically, why do that? Okay, so what you have to do here, you have to call the super constructor, and you have to call it in this particular way. You have to first give the type of the component, you then have to pass the name, you then have to pass the arguments, which are none basically for component resources, because you don't have to provide any arguments for component resources, and resource options as the last argument. Then you declare your resources that are part of this component, but there's a gotcha. You have to pass, as one of the resource options, you have to pass parent this. So you have to self-reference this component resource as the parent of that resource, or Pulumi won't know that this component is the parent of this resource. And that is quite important, because if you then try to, let's say, change that or destroy this component, the ordering is related and managed by the parent relationship. So if you drop that, it's a problem. And there is no type checker to tell you that you dropped that. And then there's the third thing that you have to do. You have to call a method that is declared on the component resource, which is called register outputs. And you just use the lifted syntax here and just output the bucket domain name. So that's how it works in Pulumi.js. That's how it looks like in Bison. So you just create a case class. It basically extends the component resource because we wanted to stay similar to how Pulumi APIs work, but component resource is just a marker trait. It doesn't do anything. There's no logic in it. And you have this function called component, which is a nicely typed API. You have to pass a non-empty string. You can't just create a component that has no name. So we already take care of that. You have to pass a non-empty string. Then there's a macro that checks that this type is correct Pulumi type. It has to have the structure, or you will get a runtime error. You don't get runtime error with us, you get a compile error with us. And then you have the lambda that you have to pass to it, but you don't have to remember about passing the parent because of the implicit scopes that we get with Scala. We automatically propagate the changes to the parent, so the bucket is already a child of the component. And the only thing that you have to do, you don't also have to remember to call the register outputs on that, because we are taking care of that with generic derivation of a type class for the my component that happens automatically. So finishing notes. Where are we with this? We are reaching basic parity of the features with other Pulumi SDKs right now. The component API is a draft that is being implemented. I started working on that yesterday, basically. Our efforts are currently directed towards solving issues with huge jars that we have to build for provider APIs. And that's, to be honest, the biggest problem that we have to deal with. We got away with small coverage of the code base, thanks to Scala and thanks to proper typing of the project. So it would be good to have more coverage, and we have to write more tests. And we assume that the first public beta will be released at the end of this month or at the start of the next month. So the last things that I want to touch, I'm letting you to go to lunch, no worries. We want to do nice things with Bison. We want to integrate it very closely with Scala tooling that we work on and we maintain. So we want to provide a more seamless experience for Scala developers, and we want to give them the ability to work on full projects, on full scope of products. So from ground, which is infrastructure, up to, if you are up to Scala.js frontends, for instance. My personal goal is to shield the tooling team so long that they will allow me to modify Scala CLI, which is becoming currently the main Scala runner, so that it works kind of like Git. Git calls git commit command if you enter git space commit. That is my idea. I wanted to work in a way that we can just say Scala infra up, and we get a fully built, compiled, type-checked project that is deployed to a cloud environment of your choice. We also want to resurrect the infrastructure as types project, and we want to build more complex libraries of components that are fully typed and have well-typed interfaces between them. So it's impossible to connect service or client that calls HTTP to gRPC service, because it doesn't make sense. It shouldn't be possible. Why are you trying that? It should be just in types. And we want to do that all in Scala. We want to have full stack. We also have a prototype that we are very happy about, which is a quite radical idea. We want to put lambdas into infrastructure programs. We want to put definitions, kind of like Spark. So definitions of lambdas would go into a Pulumi program, and they would be, by means of magic and metaprogramming, separated from the project, extracted as a separate project, built, deployed, and the deployed lambda would be managed by Pulumi. Pulumi has this capability already. It's called Magic Lambda AWS for AWS, and it only works with Pulumi.js, mostly thanks to the toString on JavaScript functions that returns the source. So yeah, we have metaprogramming. We are doing that a better way, and we already have an SDK for AWS, a complete SDK working with Scala native. So on another conference, one of the compiler team friends of mine, Wojtek, presented lambdas that are running on AWS with full support for AWS SDK, compiled to native binaries via Scala native, and running in sub 15 milliseconds range. They were actually running, it was a quite simple lambda, it wasn't doing much, but after warm-up, it ran in 5 millisecond range. So we are hyped about that. We want to allow you to do stuff like that. So I think that's the last thing. Yeah, it is. Thank you so much.
Thanks, Łukasz. Great talk, by the way. We run out of time, so we maybe only one question from our audience.
Cool presentation. It seems like you have to do a lot of work to wrap some sensible semantics around Pulumi. Now, you mentioned that the output or the result type has monadic semantics.
Yeah.
Is there some approach to also have an applicative semantics that I can compute all the resources that I'm going to need before actually running and creating the resources?
So basically zipping. Yes, it has zip.
But can I enforce that in my program that it's not running?
What do you mean enforce? By enforce?
I mean, I can probably create a situation in my program where before I see what the rest of the code is going to do, I need to create some resources, right? So my question is, can you constrain the Scala SDK in a way that it will give you the plan first and then run everything instead of having the Pulumi semantics of like creating the stuff while it's being run?
Okay, so there's one thing that I didn't mention. Pulumi has dry run built in. So the first thing that Pulumi program does, and that's one of the problems that you have to deal with the output data structure, and why everything is optional inside of the output, is the fact that when the dry run happens, no values are being passed by the program. It just goes through the program with empty values and checks what you are declaring. And it checks against the state, it checks against the infrastructure that it knows that exists. And only after dry run has completed and your program works, didn't fail, it only then asks you, we are going to do these changes because we have a diff between what you have declared right now and what exists. And when you do that, you see the diff and you make the decision, yes, apply that, or not. And if you're talking about, just applicative semantics and just code, you can zip things, and you can also enforce dependencies between resources by one of the resource options. So you can say that, okay, this bucket, if we do this way, as I've shown, they are done in parallel. But you can enforce ordering by either, evaluating them as monadic code, or just using depends on resource option. If you do resource options, it makes sure that whatever the ordering in the program was, however it was evaluated, ordering by the engine when creating resources will happen in correct way.
Okay, thank you for coming, and let's give a big round of applause for Łukasz.